According to the U.S. Energy Information Administration, over half of the energy consumption in a residential home comes from heating. The rate of energy consumption obviously peaks at winter and summer weather. Even in a day-to-day basis, energy peaks are caused by humans' need to maintain a comfortable temperature. The reality of a static and continuous system makes intermittent, renewable source of energy not practical in replacing out fossil fuels. The issue here is in energy storage. The main advantage of fossil fuel plants is that their outputs can be controlled since their energy source can be stored for long periods of time. Many have looked at researching longer-lasting electric batteries, but there is a large community experimenting with the viability of thermal storage technologies. In particular, phase change materials show promise in providing a way to store thermal energy throughout the year. An example of an application for PCM can be seen on commercial heating pads, retaining a constant temperature for a long time. Phase change materials, PCM, all share a characteristic of having a large enthalpy of fusion. What this means, it takes relatively a lot of energy for the material to go through a phase transition from solid to liquid and vice versa. This property of PCMs allows it to absorb and release more heat without changing temperature. This increases the thermal inertia of the material such that it's less responsive to sudden temperature changes outside its system. In the paper of Stutz, it was stated that PCMs can be integrated into the wall to store more energy in the same storage volume. A 2.5 cm hydrated salt PCM can store as much energy as a 15 cm concrete wall. One application of thermal storage can be applied in creating a solar wall in residential homes. A solar wall uses PCMs to maintain a comfortable temperature in homes by efficiently storing heat. Another application involves the use of thermal solar collectors, which, along with a working fluid exchanger and PCM, allow one to store excess energy generated during summertime to be used in wintertime. In the paper of Kilumpu from Cape Peninsula University of Technology, South Africa, the focus on thermal storage lied in the optimization of the system to make it more accessible in his country. He investigated the thermal efficiency of 3 different mixtures of paraffin wax. In this study, the 3 different paraffin waxes are chemically stable, non-poisonous, and non-corrosive over a long period of time. The temperature difference between the outlet and inlet became the basis of calculating the rate of heat being transferred between the work fluid and PCM in the heat exchanger. Both a high latent of fusion and thermal conductivity improved the performance of the PCM being investigated. After a comparison of the results, RT27 presented more advantage due to bigger amounts of heat stored and released by the PCM, and hence higher efficiency with the different HDF's flow rates compared to RT25 and RT35, shown in Table 2 to 4. Also, RT35 have both a low latent heat of fusion and higher melting point, which performed better for higher working fluid flow rates. Essentially, different properties of PCM became more prominent depending on the demands imposed on the material. The experimental results showed the practicability of using PCM as storage media for solar collector heat storage systems. The patent on a number of thermal storage systems is attributed to the following inventors: Byron Craig Owens, Jeffrey Neil Cox, Peter Franz Howarth, and Riyad I. Sawafta. The owners of the patent currently head a company called Phase Change Energy Solutions. Their company focuses on improving the energy efficiency of living structures. The patent is on the design of a mobile thermal storage system with a casing of a shipping container. The interior houses a thermal transfer disk with a helical-shaped heat exchanger with a number of pipe segments ending outside the ship container. The PCM occupies the majority of the interior shipping container. Today, PCES operates a 100 square feet R&D and manufacturing facility in Asheboro, North Carolina. Positioned in one of the most research-rich communities, PCES has become a global leader and a recognized manufacturer of next-generation phase change products and thermal storage solutions using its proprietary technology platform, BioPCM. And finally, in a Philippine context, PCM can be applied to improve the performance of geothermal resources present in the country. It can save energy costs due to heat loss present in existing geothermal system. PCM can be attached throughout a geothermal plant to recover waste heat in the system. Also, locations that were not economically viable as a geothermal plant may be redesigned to use PCM as a passive source of thermal energy. Marginal fields of geothermal energy become easier to tap using portable systems of heat storage. The increase in exit temperature reflects an increase in useful heat loss. In terms of the second law of efficiency, the decrease in ambient temperature causes an increase in energy loss to the atmosphere. Surely the application of energy storage can provide a means of saving energy, which can be used in the off-peak times when demand is low. In conclusion, energy efficiency and energy storage is a growing concern for the energy production industry. PCM provides an alternate approach in addressing this issue by focusing on heat storage systems.